Okay, good afternoon, everyone. It is 2:05, so I'll start lecture. All right. Okay, so today is going to be my last lecture for this module. Um, Next week is going to be your quiz. Okay, your quiz, just to remind you, I've already told you all the information, but just to remind you, the quiz has 25 questions. Okay, 25 questions. They are MCQ, multiple choice questions. Means you have a selection of 4 choices, A, B, C, or D. Okay, only one can be correct. Okay, some people say 2 answers correct. So okay, only one answer is correct. Okay, so please select wisely, and the quiz will be conducted online. Okay, so online means on Canvas. So if you go to Canvas, there's actually this tab, quiz. I have not set it up yet because the quiz is next week. So if you go closer to the quiz date, maybe the day before, you might be able to see this link where you can click on the quiz. If you don't see, don't worry, okay? On the day itself, you will certainly see it, okay? So it's all a matter of me uploading the questions onto the platform, right? So I'll upload the question just the day before. I don't want to upload too early in case someone hacks into my account or something. All the questions. Okay, I don't want to upload the quiz too early. So on the day itself, you should see it. The questions will be jumbled. The answers will be jumbled as well. So there's no point if you sit beside another person and try to do the quiz together. You will get different questions, different choices. Okay. In fact, it will probably slow you down rather than help you. Okay, if you try to sit with someone else to do the quiz. So don't do that. Okay, do it. Earn the marks by your own credits. It's open book. You can use anything except another person's help. So don't get someone to sit beside you and tell you how to answer as well, because that's getting someone else help, right? That's cheating. Cheating is, of course, a very serious offense in NUS. Well, we've seen cases where people really get expelled because of that. Okay, so you don't want to do that. Okay, it's not worth it. It's not worth it. Okay, so don't cheat. And to prevent that from happening, you are supposed to go on Zoom and open your video. Okay, then I can see what's behind you, what's beside you. Okay, so this is the invigilation mode. Okay, the Zoom link again will be on Canvas. Okay, you'll see a tab, Zoom or something. Okay, you can click on it and then you can enter Zoom. Okay, please have a computer with a video screen. Okay, don't use a black screen. I need to be able to see you. All right. Okay, so again, it's just a reminder of whatever I told you in the first lecture. So before we start lecture, any questions on the quiz? Because I think that's probably quite important for many of you, right? To get good grades. And any questions that you want to clarify about the quiz? Don't need to be shy. Okay, all quite clear. Okay, it's 33%, by the way. Okay, 33% of your grade. All right. In that case, I'll start lecture proper. All right. So today is going to be more of a seminar style kind of lecture, because I've already taught you very basic principles of semiconductors. I've taught you basic principles of quantum mechanics, right? So the foundational knowledge that you need is already built up. Okay, so today we'll try to build on that, and we'll talk about Perovskite Semiconductor. Now, why perovskite? You might be asking. I mean, of all the inorganic electronic materials, why do I want to talk about perovskite? Okay, because it's new. All right. You guys are graduate students, masters, PhD. We are supposed to be looking at new technologies, something that is an improvement to the past. I'm not saying that perovskite is certainly better than what we have in the past. Okay, but it's new, it's novel, it has good qualities, and it's worth studying. Okay, so there's a lot of research groups in the world that's spending resources and time to study this material for good reasons, including our own group. Okay, we also study perovskite because you will see later. I'll explain. There's a lot of good qualities of the semiconductors, but just to be mindful. Okay, there are also problems. Okay, so it's not a bad thing actually. To have problems means there's opportunities for you to solve, right? If a material has no problems, then there's nothing for all of us to do, right? I don't need to Okay, so I'll list out the problems as well. Something for the graduate students to think about. If you want to do research in this area, you can think about whether you have a solution or have an idea, right, to solve these problems. So it's a reasonably new and emerging field. The industry is investigating whether to adopt it or not. Not yet mature. Okay, so don't say, oh, this is in all our televisions now. It's not, right? It's just emerging. Okay, but it's precisely because it's emerging is exciting. All right. Okay, so just to give you a brief historical background, as always, I think it's important to have a background of who discovered what and when. Okay, so perovskite is actually a term that is used to describe a very general class of materials. Okay? In fact, it started off with a non-semiconductor. Okay, it started off with a non-semiconductor called calcium titanate. Okay, calcium titanate is an oxide, right? CaTiO3. It's an oxide. It's insulating. It's not used as a semiconductor. Okay, and also not the kind of semiconductor that I'll be explaining to you later. Okay, it's just really started off as this chemical called calcium titanate, this mineral called calcium titanate. Okay, and this was discovered in 1839 in the Ural Mountains of Russia. Okay, this was discovered by this mineralogist called Gustav Rose. His portrait is here. Okay, so this guy here, Gustav Rose, discovered this mineral calcium titanate. But somehow he decided not to name it after himself. If not, might not be calling it perovskite. Okay, so he decided to name it in the honor of this guy here. Okay, this guy Lev Perovsky. Okay, this is I suppose a rather famous and influential Russian mineralogist, Lev Perovsky. So he decided, okay, let's name it in his honor. So this is called perovskite. Okay, this calcium titanate is called perovskite. How does it look like? It looks like that. Okay, it's crystalline, of course. It's a crystalline oxide. Has insulating properties. Um, but not the kind of semiconductor, not precisely the semiconductor that we are looking at. Okay, turns out that we call our semiconductor perovskite because it has a similar crystal structure. Okay, the reason why we call it perovskite is because, well, it has this crystal structure, so it is perovskite. Okay, our semiconductor is perovskite because it has this crystal structure, but not this chemical formula. So talking about crystal structure, then what is the crystal structure of perovskite? Okay, you see two unit cell. I can't remember if I told you about unit cell, but okay. Anyway, a unit cell is the smallest repeating unit of a crystal. Smallest repeating unit. But you see two unit cells or two crystal unit cells here. What does it mean? Actually, they are the same. They are just drawn in a different way. Okay, let me explain how. Okay, let's take a look one by one. Okay, let's take a look at this. The top one. Okay, this calcium titanate has a stoichiometry of 1:1:3, right? Calcium 1, titanium 1, oxide 3, right? So there's we can write the general formula as ABX3. Okay, that's just a general formula, right? ABX3. A is a large cation. Cation is a positive ion. B is a small cation. And then X is an anion. Anion is a negative ion. Okay, so we have we have two positive ions and three negative ions, right, in this crystal. Now, if you look at how it's arranged, the smaller cation is in the middle of this unit cell. Okay, and the larger cation is at the corner of this cube. Okay, and then you see there's this anions all around, right? Okay, so this anion, it actually forms an octahedral coordination to the center cation. Octahedral. Are you all familiar with the term octahedral? Octahedral means 8 faces, right? If you see, if you look at this structure here, it has 8 faces, right? There are 6 points, 1, 2, 3, 4, 5, 6 points that forms this structure called octahedral and has 8 faces. Okay, so this octahedral coordination is a 6-fold coordination because there's 6 anions, right, coordinated to a single cation. Okay, this is one way of drawing it. Okay, so this is one way of drawing it. But now if I want to draw it another way, I can put the large cation in the center of this unit cell. Okay, and I put the small cation at the corner of this cell. Just a different way of drawing it. All right, if you like, actually, I'm just draw it differently, right? In this case, okay, and then if I draw it this way, I would see this structure. Okay, in this structure, the large cation is in the center, and the corner becomes the smaller cation. Okay, the corner becomes the smaller cation. Okay, and if you try to imagine, right, if I draw it this way, then all the anions surrounding the center, there would actually be a 12-fold coordination. Let's count. The center, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12-fold coordination of the center. They are identical structures, just drawn differently. Okay, so if you see papers and you see this is a perovskite structure, doesn't look like, that doesn't look like this, looks more like this, well, it's the same thing. Okay. All right, so that's about the crystal structure. Now, turns out that perovskite can only form under certain conditions. Certain conditions, meaning when the ions have certain sizes. Okay, so when there's a mismatch in the sizes of these ions, then the perovskite structure is not stable. It doesn't like to form. It forms some other crystal structure, right? Non-perovskite ones. Okay, so what's the condition? Okay, the condition that they have a size ratio. They have a size ratio that is calculated by this formula here. Okay, and this number should be close to 1. Okay, I'll tell you all the different cases. Okay, so if I calculate all the sizes here, I substitute a radius of A cation, radius of B cation, radius of X anion. I substitute all these numbers in, I should get a value here that is close to 1. And then I get the perovskite. Okay, this formula here is called the Goldsmith tolerance factor. Goldsmith tolerance factor, of course, formulated by this guy called Goldsmith. Okay, so he calculated these numbers and he came up with a few conditions. You will see here, okay, in this table here. Now, like I said, if it's close to 1, right, 0.9 to 1, then it forms a very nice cubic perovskite structure. Very nice cubic perovskite structure. A and B basically have good sizes, right? Good sizes fit into this perovskite structure. Okay, what happens if the number you calculated here is more than 1? More than 1 means what? Your radius of A is a little bit too big, right? Because it's at the top here. Okay, so A ion is too big, or of course you can also say, okay, B ion is too small. Okay, so in this case, what structure does it form? It forms a distorted structure. It could be a hexagonal structure, it could be a tetragonal structure. Okay, these are basically distorted. Means that this doesn't look like a cube, right? It looks distorted. It's not a crystallography class. I shall not go into what all the different crystal structures look like, but just know that okay, if it's not close to 1, if it's bigger than 1, it's going to be a distorted structure. Of course, it can also be smaller than 0.9, right? It can be smaller than 0.9. So if it's 0.71 to 0.9, it forms an orthorhombic or rhombohedral structure. Again, this is a kind of distorted structure, so it's not cubic. And what does it mean? It means A is too small, right? Because it's now less than 0.9. So A is too small, not ideal. Now, of course, you can also say, oh, B is too big. And finally, if it's very, very much lower than 1, let's say 0.71 and below, then it does not even look like a distorted perovskite structure. It completely does not form any structure that resembles this. No longer just a distortion, it's actually a non-perovskite structure. And of course, then you don't get a perovskite, so there's no point talking about perovskite. This is not a perovskite anymore. Um, Now, like I told you, this perovskite that I'm gonna introduce to you is a semiconductor. It has a lot of interesting properties. It's new, but like I also said, perovskite is just a crystal structure, right? It's just a name for a crystal structure. So what can we do with other types of perovskite? Not the semiconducting one we are talking about, right? What can we do? A lot of things. Okay, I don't want you to walk away from this lecture thinking that, oh, perovskite is only a semiconductor, it cannot be used for anything else. Okay? A lot of utility, there's a lot of applications for other types of perovskite that actually we already use in our daily life. Okay, so this is just a brief introduction, right? I'm not going into detail here, but it's a brief introduction of what other types of perovskite can do. Okay, number one, piezoelectricity. Piezoelectric is when you apply a stress, a mechanical stress means I press it, right? You apply a mechanical stress to a material and it forms a voltage. Okay? And this type of materials, the reverse can also happen. I apply a voltage to it, it creates a mechanical stress. So, well, there's many use of it. I mean, young people here, maybe you go on dance floor, you step on the dance floor and mechanical pressure, right? And then you see all the lights coming on and things like that. Okay, so this could be, for example, a piezoelectric function, right? You using mechanical strength to turn it into electrical generation, right? In this case, in this case, you're converting mechanical stress to electrical energy and then subsequently maybe to light energy, right? So piezoelectric. But of course, the reverse can also happen. You can use piezoelectric as a motor. That means now I apply a voltage, and this voltage creates a mechanical stress, which can be translated into motion, right? So, for example, for those of you who like photography, right, you have a lot of lenses. This is a piezoelectric motor, right? But like your big DSLR lenses, piezoelectric motors, it's very silent motors that is very precise for you to focus your lenses. Okay, this is piezoelectric material. And how do we um, make this kind of materials? What do we make it from? Perovskite. Okay, so a lot of perovskite like barium, titanate, PZT, they have these very interesting functions. Okay, next, ferroelectricity. Okay, ferroelectricity is when this material has a spontaneous electrical polarization. That means even without me having to apply a voltage, okay, this material is already electrically polarized, okay, as a plus and minus, like this material. Okay, of course, I need to first pole it. I need to first pole it to have this polarization. But like a magnet, right? You can create a magnet, but once you create this magnet, you leave it there, it naturally has this magnetic property, right? Without you having to do anything to it. Okay, same thing here. Okay, once I create this ferroelectric material by poling, then it naturally has this electrical polarization. So what can we use it for? As you can imagine, it's very useful for memory because if I apply a voltage, now it remembers that the voltage, memory, right? It remembers, it now possesses spontaneous electrical polarization. I can use it for memory, right? I can use it for capacitors as well. Again, it's utilizing the memory effect of this electrical polarization. And the reason why it's called ferroelectricity is probably inspired by ferromagnetism, right? Ferromagnetism is your magnet has magnetic property, like iron is ferromagnet, right? Made into a ferromagnet. Okay, so same thing here. It has a spontaneous electrical polarization. That's why it's called ferroelectric materials. Examples of perovskite that possess this property: barium titanate, lead titanate. Okay, next, high temperature superconductivity. By high temperature, we don't mean like 100 degrees Celsius or something. Okay, so in fact, recently superconductors have been in the news a lot, right? I mean, partially because of fake results and things like that. Okay, but high temperature superconductors are actually very important technologically. I'll tell you why later. Okay, but basically, high temperature superconductor operates even at very low temperature. Let's say above minus 100 degrees Celsius, right? Already that's very high, right? Anything that's even close to 0 degrees Celsius is already very high temperature superconductor. So turns out that many perovskite has these promising properties. Okay, so lanthanum, barium, copper oxide, for example, is considered a high temperature superconductor. What can we use it for? For levitation, right? So you all know that you can create magnets by electricity, right? So do you all know, like, if you go into the MRI machine, those in the hospital, you go in the MRI machine, you actually go into a machine which is a giant electromagnet. How does electromagnet work? Right hand grip rule. Okay, you have a circular current that produces a magnetic polarization. Right? Right hand grip rule I already taught you in the first lecture, right? Okay, so you can actually create a magnet, okay, with this right hand grip rule by running current in a circle. Now imagine for normal materials, if you run a current like that, there's resistance, right? Resistance means what? You generate a lot of waste heat. It expends a lot of energy that does not need to be expended. It just create heat. There's no use to the heat, right? Now, if you have a superconductor that has zero resistance, then this can go on forever. So next time your MRI machines, if you ever discover this kind of superconductor, your MRI machine will run at very low electrical power, right? You don't need to spend a huge amount of energy just to run a huge electromagnet. And this has implications every industry, right? Including trains, right? You can have trains that levitate and therefore no resistance, right? Simply by running the tracks or maybe the train tracks with electromagnets. Okay, so it's a very novel, futuristic technology, but unfortunately, we still have not discovered such a good material yet. But promising, okay, promising. Okay, next, magnetoresistance. As this term suggests, magnetoresistance means that this is a material where the resistance changes with magnetic field. So that means I apply magnetic field, its resistance change. Now you might be thinking, okay, what's it useful for, right? I apply a magnet, the resistance change. So what? You all know that for most of your devices, your computers, you actually have a magnetoresistance, right? That's why your hard disk drive is actually a magnetic device. Okay, your hard disk drive actually has tiny little dots inside that is magnetized, not magnetized, magnetized, not magnetized. How do you think these are read? These are read. How do I read that you have magnetized, not magnetized, magnetized, not magnetized? Right? So I have a head, I have a reading head that goes in a circle, and as it goes to a magnetized area, my resistance change, and then I go to the other area, the resistance change again. So by reading the current, I can then convert this to what? 1010111000111100, right? Okay, so you have in your magnetic hard disk one of these magnetoresistance material. Okay, and what contributes or what gives this magnetoresistant properties? Perovskite, right? Lanthanum, magnesium oxide. Okay, so that's magnetoresistance. And finally, ionic conductivity. It turns out that there's many perovskites that have good ionic conductivity. That means ions can move across that material. Ions can move across this structure. And nowadays we are in the EV age, right? Especially, I guess, in China, there's a lot of adoption of electric vehicles, right? EV means what? Batteries. Need batteries with good ionic conduction. What material has good ionic conduction? Perovskite, right? Lanthanum, aluminum oxide, lanthanum, gallium oxide. Batteries, of course, beyond batteries, you can use it for fuel cells. Fuel cell is still under research, I guess. I mean, of course, there are fuel cells around already, but for mainstream consumer use, not yet. But batteries certainly a lot. Right? Every one of us has a, even in our laptop, tiny battery, right? Okay, electrochemical devices, sensors, and so on. Okay, a lot of these uses ionic conductors. Okay, so I guess it's not really a waste to tell you all these things because these are all what? Inorganic electronic materials. Okay, these are all belong to the class of inorganic electronic materials. Well, I guess just not specifically to the semiconductor that I'm going to tell you about. Okay, so I hope you have a better appreciation of what other kinds of electrical applications we can. Okay, so now that I'm done with that, okay, let's go into the perovskite that we want to talk about, right? As a semiconductor. Okay, this type of perovskite is discovered. Actually, I'll tell you the history later because I have some slides on it. Okay, discovered very long time ago, but it only recently became quite popular. Now let's take a look at the structure first. Okay, let's take a look at the structure. Okay, you see, this is of course the perovskite structure that I've already introduced. Okay, but what is the cation inside? First, you have a methyl ammonium cation. Okay, some might be thinking, okay, it's not exactly organic, right? Organic cation. It's okay. We can also use an inorganic one, which later I'll tell you is, for example, you can use cesium, you can use rubidium in place of this methyl ammonium. But for this case, we call it a hybrid material. So hybrid material means it has both organic and inorganic components. Hybrid perovskite. Now, methyl ammonium is the cation at the corner of this unit cell. In the middle, there is a lead cation, Pb2 plus. Okay, lead cation. And in this octahedron, the anion can be a halide. Okay, in this case, I wrote iodide. Okay, but actually it can be any halide. It can be iodide, it can be bromide, fluoride. The only example that I have not really seen is fluoride. Okay, nobody uses fluoride for this. Okay, but chloride, bromide, iodide, no problem. Okay, so we have this perovskite structure with this chemical formula, right? One of this, and three of this. All right. And if you try to balance the charges, you will notice that actually the cation here needs to be monovalent. That means only one plus charge. The middle here, two charge. Okay, so divalent. The divalent cation, typically lead. There are some people who like to do research on tin plus as well. Okay, but it's not so stable. Plus is not so stable. Lead is better. Center cation is typically lead 2 plus. And then the three halides, like I said, can be bromide, chloride, or iodide. Okay, any of these three. Now, it turns out that this is soluble in polar organic solvents. For example, DMF, DMSO, GBL is gamma butyl lactone. Okay, these are all very polar organic solvents. Okay, and of course, I gave you a question last week or the week before, right? What kind of bonding is this structure? Okay, ionic bonding. Okay, this is held together by ionic bonding. So ionic bonding means that polar solvents is very good for dissolving ions. Okay, so EMF, EMSO, GBR. And you can use this, dissolve it in a solution, coat it into a film. The film looks like that. The fact that it's colored is very nice because it's colored means it absorbs light. And of course, later on, people found out that this light absorbing film with perovskite is actually a very good semiconductor for solar cell. So I absorb sunlight, convert it to electricity. Okay, I'll tell you more about this later. Okay, but one of the first useful applications is solar cell. Okay, let me ask you a question, just to wake you up. So, which are the methods that I can use to change the band gap of this perovskite semiconductor? You all understand band gap now, right? You all understand semiconductor now, right? What can I do to change the band gap? I haven't activated yet, so if you have trouble, okay, now it's on. You can. Most of you have answered. I'll give you 10 more seconds, okay? So for those who want to submit, 10 more seconds. 35% thinks A, and then slightly more than half thinks B. Okay, so that means some people think 3 is not an option. Okay. So all of you agree, or most of you agree, that you can change the halide anion to change the band gap. Okay, yes, that's correct. Okay, you can change the halide anion. A lot of you think also you can change the divalent group 4 metal cation. Basically, change the lead 2 plus, right? Pb 2 plus. Say change to tin, Sn 2 plus. Yes, you are also correct. Okay, now change the size of the perovskite crystal. Yes or no? Okay, the answer is yes. Okay, so that is related to the concept of quantum dots, right? So remember when we're talking about quantum dot is where the crystal size is smaller than the Bohr exciton radius. Right? In this case, we create what? Quantum confinement. Then you have the particle in the box theory coming in, right? Now you have quantum confinement, particle in the box theory coming in, your band gap. So you can change it by the size of the crystal. I'm quite specific. Below 10 nanometers. Okay, that's the Bohr exciton radius. If I say below 10 microns, okay, then that's not an answer, right? Below 10 microns is still very big. Okay, so you need it to be small, right? Really small. Then you get quantum dots. Very good. So, how do you prepare these perovskite films? It turns out there's many ways to do it. Okay, there's really many ways to do it. I'm going to introduce very broadly, right? Very broadly, the few main principles of creating this material. Of course, you will see in papers there are slight variations here and there. Okay, but there will be variations of whatever I teach you. Okay, first solution, most popular as well. Okay, most popular solution process. So remember, is perovskite is a combination of ions, right? Combination of types of cations and one type of anion. So what I can do is I can just make a solution that has all the ions, right? I make a solution that has all the ions. So how do I do that? Okay, firstly, I need methyl ammonium. So I need to synthesize this methyl ammonium. Methyl ammonium is actually just a salt of a base and an acid. The base is amine or methyl amine. You all know that amine is a base, right? It's a weak base. Then I react it with a strong acid, which is hydroiodic acid. Then I form a salt, right? Methyl ammonium iodide. Okay, so by doing this, I already create what? Iodide ions, methyl ammonium ions, right? So very good. I have two types of ions. All right. Then I add into lead iodide. Lead iodide contains another two types of ions, which is lead and iodide. I mix them all together in EMF. They all dissolve. Okay, and exactly I would have a stoichiometry of 1 is to 1 is to 3. Okay, if I reaction. Once I create this solution in DMF, it's a very polar solvent, dissolves all the ions. Once I create this solution, I can do what we call drop casting or spin casting. This might not be familiar to some of you, but of course, I think some of you would probably have heard of this. What is drop casting and spin casting? Okay, let's start with the easy one. Drop casting. Drop casting means you drop the solution and let it dry. Right? What is that, right? Drop casting means you drop the solution on something and let it dry. And once it dries, it forms a film. Okay, that's very simple. Okay, what is spin casting then, or spin coating? In this case, you drop a solution and you spin the substrate. Now, as you can imagine, as I spin the substrate is what you put on. Okay, if you spin the substrate, then the solution is going to spread out, right? It's going to spread out evenly, and then in fact, some of the extra ones will be flung off outside. And what you create is a very smooth film, very smooth thin film. Okay, so perovskite films are very frequently created by spin coating because in this case, I drop the solution, it coats, spins off, dries off, creates a very thin film, very thin and smooth film. Okay, so spin casting or drop casting. The process is shown here. Okay, this is typically a glass substrate that you drip your solution on, and then this thing spins. Just spins off the solution. And finally, there's one more step actually to heat anneal it. Basically, it's like baking it. Right? You put it on a hot plate, heat it up. What's the point of heating up? To allow the ions to rearrange itself. It gives it some energy for it to rearrange itself and pack nicely into a crystalline. Okay, so this is the final step, heat annealing. Okay, and it looks like that when it's formed. Again, a brown colored film. That is a very good semiconductor. Right? So that's one way of doing it, solution. The second way of doing it is what we call a vapor process. It's also quite similar in the sense that you use the same ingredients. Okay, but of course, in this case, you use a vapor, you don't use a solution. Okay, let me explain. In this case, you will put methyl ammonium iodide, which is this one. Okay, methyl ammonium iodide into this heater. We call it a sauce, right? Sauce because it's the source of the vapor, right? It's organic sauce is the source of the organic vapor. You put this material into a heater, and then you put this lead iodide into the second one, into the second heater. Inorganic because lead iodide is inorganic. Okay, and then you evaporate on not evaporate. You apply a vacuum to this chamber. You apply a vacuum to this entire chamber, so this chamber becomes in a high vacuum environment. And we're talking really about very good vacuum levels like 10 to the power minus 6, minus 7 millibars. Okay, very, very low pressure. Okay, so now under very low pressure, I will heat up these two sources. I will heat up these two sources. And when that happens, the material evaporates. Okay. If you like, you can also call it sublimes. Sublimes means turning from a solid into a gas, right? Sublimes. Okay. So it sublimes. That means there's a gaseous cloud of ions here. There's a gaseous cloud of ions here, waiting to deposit somewhere. Okay, so where do you put your substrate? You put your substrate at the top here. Your substrate is cool, so it will deposit onto your cool substrate at the top. Because if you want uniform, if you want the substrate to be uniformly coated, you can actually spin the substrate. That's why there's this spinning action here. Okay, and turns out that this method can also prepare very good perovskite films. Okay, so that's the vapor method. All right, so whatever I've described to you is two ways of making what we call bulk films. Bulk films means large area, reasonably thick films of a few hundred nanometers. Of course, not microns. In terms of semiconductor terminology, a few hundred nanometers is already quite thick. Okay, so reasonably thick films and very large area films, bulk films. Now, there are also another group of perovskite researchers that like to deal with nanocrystals for good reasons, right? I can control the band gap. I can make them very colorful, like quantum dots. Okay, so this group of researchers, they like to synthesize perovskite nanocrystals. Actually, if you remember last week, I brought in quite a few bottles of samples, right, in all these solutions. Those are perovskite nanocrystals. Okay, perovskite quantum dots. Looks like that, right? Looks like that. Okay, so there's actually two main papers. I mean, essentially, they are very similar concepts. There are two main papers that describe the synthesis of these perovskite nanocrystals. I'll cover that. The paper on the right is a bit more popular because it's a bit more colorful, but it's actually a bit later. So in academic world, people usually value the first paper published, right? Okay, so if you want to go back to who is the first one to actually publish this, is actually the group here, okay, by Smith and Perez Prieto. Okay, so they published this in JACS on how to synthesize the very first perovskite nanocrystal. Okay, let me explain to you how it works. Okay, to make a nanocrystal solution, you need a few ingredients. Of course, you need the perovskite precursors, okay, which is well, methyl ammonium iodide, methyl ammonium halide, right, and then lead. You also need a solvent, right, because you need this to be in solution. One extra ingredient you need is ligands. Like ligands are just like surfactants. Surfactant that allows nanocrystals to be stable and soluble in solution. So how does it work? These ligands are actually long chains, long alkyl chains, and you know that long alkyl chains are makes them soluble in organic solvents, right? There's long alkyl chains, and there's typically a coordinating group to the crystal surface. The coordinating group is either amine or carboxylic acid. Okay, so in this case, in this paper, they use two ingredients as ligands. Oleic acid is basically a carboxylic acid uh, with I can't remember 24 carbons. Okay, or 89. Sorry, I can't remember. But very long chain carbon. Okay, with a carboxylic acid end. Okay, and then they also use this octyl amine. Okay, this one very clear. Eight carbon eight carbon atom chain with the amine group. Okay, so now this carboxylic acid group and the amine group will coordinate to the surface of this crystal and allows the entire crystal to be soluble in a solvent, in organic solvent. Okay, so basically, the first guys who synthesized this, they mix all these ingredients together, right? Again, lead halide, methyl ammonium halide, the ligand oleic acid, the ligand octylamine, uh, and basically they have a warm solution. They put it into an anti-solvent to precipitate out that tiny little crystals. Once these tiny little crystals precipitate out, okay, then they can collect it, okay, and disperse it in an organic solvent. Okay, so the anti-solvent is acetone. Okay, so typically these methods of preparing nanocrystals, well, I mean, I can go on. My lab does a lot of these synthesis, but I can go on about all the individual steps involved. But I want you to just learn the central concept, right? Central concept is you mix all these ionic ingredients with the ligands in a solvent and let them crash out into tiny little crystals. Let them precipitate out into tiny crystals. You can collect it, purify it later, use it later. Okay, so it's just a general principle. All right, this is exactly how it looks like. Okay, once it's formed, it's very luminescent, same as those that I showed you last week. Very luminescent. These guys, they did it with the bromide version, which is green emitting. Okay, they didn't try it with a range of halides. Okay, so there's only one color. Okay, but about 1 year later, okay, this group of Protesescu and Kovalenko, they did something slightly different. Okay, one thing that they did different is they did it with a whole range of halides. Okay, so you can see all the colors here, right? Remember, you can tune the band gap of perovskite by changing the halide, right? So they change the halide from iodide to bromide to chloride or mixture of these halides. Okay, they got a whole range of colors. Very beautiful, right? Very beautiful work. Um, and the procedures are slightly different, but it follows the same principle as what I've taught you. Okay, procedures are a bit different. So what they did was they used cesium oleate, so that contains cesium, and oleate is just oleic acid, right? It's just oleic acid without the proton, right? So that's a ligand. They also use oleal amine. Okay, again, this long chain hydrocarbon with amine at the end. So again, same concept as it, right? Use an amine as a ligand, use acid as a ligand, use the cesium component, use a lead halide component, What they did was they did a hot injection. Hot injection means I mix them in a hot solution. Okay? That's why it's called hot injection. I mix these two together in a hot solution. Okay. Now, in this hot solution, these crystals grow into these colors. And again, I can go on and on about how to purify it and all these things, but not really important. What happens typically next is you put in an anti-solvent, precipitate out, wash it, purify it, and then redisperse into the solvent that you want to coat with. Okay, so that's sort of a purification process, but not that important for the sake of our module. The important thing is how to synthesize it. All right. So it turns out that this material that I've just described and all the ways of preparing it, they are very, very popular in the scientific field. Very popular in the sense, I think you guys are graduate students, you probably know the value of a nature paper or a science paper. Okay, and if you are doing a PhD, you probably aspire one day you want to be the author of a nature paper or a science paper, right? Okay. So it turns out that if you, well, at least in the past, this is just for your information, it's just 2012 to 2014, it's years, right? Within this short 3 years, you have all these bunch of papers in nature and science coming out to describe this material. So obviously, at that period of time, people are very excited about this class of materials. Okay. Why is it so exciting? I mean, it's just a new semiconductor, right? Why is it so exciting? Because it gives good performance. It's not just any semiconductor, it is a semiconductor that gives good performance. Okay, so it turns out that people discovered that this very easy to synthesize, very easy to coat material can produce solar cell and LEDs with efficiency of over 20%. And of course, you would think, 20% is quite low, right? It's not 100. Why are we caring about 20%? Everything has an efficiency limit. There's a theoretical limit to how high a solar cell can go. There's a theoretical limit to how high an LED can go. Okay, that means you can't break the limits. It will defy the laws of physics. It will defy the laws of thermodynamics. Okay, it turns out that the efficiency limit for solar cell is about 30%. We call it, there's a name for it, it's called the Shockley-Queisser limit, which I won't teach you here. But this limit is about 30%. Okay, for LEDs, there's an outcoupling limit. That means light that can come out without being guided elsewhere. It's about less than 25%. Okay, so perovskite devices can hit almost theoretical limit. Right? We're talking about already very close to theoretical maximum. And by the way, silicon is about, if you buy a silicon panel off the market, around 20%. Okay, LEDs, same. If you buy one of these LED bulbs, right, that does not have any special outcoupling design, also about 20+%. Okay, so it's already hitting the performance level of existing technology, which is great, right? It took other materials a very long time to get there. Okay, so a bunch of papers in science and nature. And this is until 2014. So of course, I will not go on. The next 10 years is even more, right? Now it's 2024. So the next 10 years, you probably have hundreds of papers. Okay, but just to be clear, these were not the first papers to describe perovskite, right? In fact, perovskite, if you like, is a rather old material. Consider from the first date that people synthesized it. The first date that people synthesized it was actually like what, 130 years ago. Very, very first description of perovskite was by Wells. Paper here, a German paper. Okay, so 130 years ago. Of course, these people, these Wells and co-workers, they didn't know that it's a perovskite structure, by the way. All they knew was that they prepared some colored solids, colored crystals, okay, has a formula of perovskite, right? SPBR3, and they basically synthesize some nice colored crystal that is different from their starting material. Okay, and of course back then, scientific papers were a lot simpler, right? They would just say, okay, by mixing this with this, at what condition I got this, right? And they reported the properties and so on. They didn't know that it's a perovskite. So back then, 130 years ago, that was the first report on perovskite. And then it took people another 60 years or so, okay, actually find out that it's actually a perovskite structure. It was probably the time when there are more so-called modern characterization technique where you can actually look at the crystal structure, probably by some form of X-ray diffraction study, things like that. So they actually discovered, oh, this material that was synthesized 60 years ago, it has that perovskite crystal structure. Okay, so this was the very first time the perovskite crystal structure was identified for this class of materials. Okay, this was published in Nature, right? I guess back then Nature was still a small journal, but now it's very popular. All right, and then it took another 20 plus years, okay, 20 plus years for them to use methyl ammonium. So we were talking about this methyl ammonium lead iodide, right? Hybrid perovskite. So it took them another 20 plus years, okay, to actually use methyl ammonium cation. So if you think about it, this material is really quite old, right? It's more than 100 years of history. Now, a bit more recent times, not exactly recent, but 99 plus years ago. Okay, in more recent times, scientists have actually intended to use perovskite for electronic applications. Okay, so back then, this period of time was when microelectronics is very hot, right? People starting to invest heavy money into computers and things like that. Right? So, of course, what the scientists will be thinking is, okay, it's going to be a next semiconductor that can replace silicon, right, or can replace any of these high-tech stuff. So they investigated perovskite for two types of applications. Number one, transistors. Paper 1999, they investigated perovskite for transistors. And this paper 1994, they investigated perovskite for LED, light emitting devices. Okay. And the type of perovskite they investigated was slightly different from what we are talking about. Okay, it's this kind of perovskite called layered perovskite. Now, what's layered perovskite? I might have a slide later. Basically, you have a perovskite layer, and then in between the layers, this is ligands, and then you have perovskite, and then in between. So it's called layered perovskite, okay, because it uses very large ligands, okay. And these large ligands are basically the substitution for metal ammonium. If you like, it's a large ammonium cation, very large ammonium cation. Okay, so large ammonium cation. By large, if you look at what is one of the examples, this is actually a phenyl, phenyl ethyl, phenyl ethyl ammonia. Okay, a benzene ring and then two carbon and then ammonia. Okay, so it's very large. Okay, so like I said, they tried to use it for two applications: transistors as well as LEDs. Although the papers are are in quite famous journals like Science, okay, the performance was actually not that good. Okay, of course back then it was new, right? It was very novel, very new and exciting, promising. Okay, but at the same time the performance was not great. Okay, so turns out that it's not good enough to replace silicon more advanced applications. Okay, so then the excitement back then died down again. Okay, so you think about it, 20 years ago, 20 plus years ago, there was a moment of excitement for this class of materials. And then because nothing too much came out of it, went down again. Okay, what about LEDs? Okay, so the first guys to investigate this for LEDs, they only managed to get it to work at cryogenic temperature. That means they have to literally put the device in liquid nitrogen for it to light up. As you can imagine, it's not well. It's a nice result. I guess nice demonstration that this can emit light, right? But not very useful, right? You need a super cold environment for these to light up efficiently. So what's the point? Okay, so again, there was this period of momentarily moment of excitement, and then after that, this wave died down. Okay, until recent days, recent years. Okay, um, I think I have the history of it. How I have the history of the recent wave of excitement, but I think that's a few slides later. Okay, so okay, let's get back to the science. Not so much of the history. Okay, so by the way, I think I forgot to mention this. Okay, this kind of halide, this kind of layered hybrid perovskite, this kind of layered hybrid perovskite has a larger exciton binding energy. Okay, because it has organic layers, right? So organic layers tend to have a smaller dielectric constant or smaller relative permittivity. Therefore, have a larger exciton binding energy. Okay, so back to the science. Okay, not so much of the history. Okay, it turns out that this metal halide perovskite semiconductor, as we have covered in the question, we can change the band gap by a few things, right? We can change the center metal cation from lead to tin, for example. Halides between iodide, chloride, bromide. We can also change actually the organic cation, okay, from methyl ammonium to say cesium. Okay, so but the impact on the band gap is greatest by changing what? By changing the ingredients of this octahedron. In other words, by changing the anion and the center cation. Okay, so the band gap is mostly determined by this octahedron here. The blue color large cations actually affects only a little bit. So band gap is largely determined by the metal halide octahedron. Now, the perovskite that became popular and to be used for solar cells, the band gap is 1.6 electron volts. If you do a calculation, this allows the perovskite to absorb a lot of light in the visible spectrum. This is why it's a good solar cell, right? Sunlight has a lot of visible spectrum. Okay, so able to absorb in the visible spectrum makes it very good for solar cells. It absorbs below 780 nanometers. Basically, and as I've mentioned, and we have gone through the question, I can tune the band gap by changing the metal or the halide anion. And just for your information, I think I've also covered this in one of the earlier questions. It's a direct band gap semiconductor. That means for this electronic transition, I don't need the wave function to change direction, right? I don't need an additional phonon. Okay, so direct band gap semiconductor means that it's very efficient at excitation, very efficient at absorbing light. Okay? And as a result of that, it therefore has a high absorption coefficient. It's very efficient at excitation, right? So it should absorb very strongly. Okay, so it has a high absorption coefficient, and that's why it's strongly colored. The film here is essentially black or brown, right? Means it absorbs most of the visible light. Okay, I think I want a break. I'm getting a bit thirsty. So let's come back in 5 minutes. Okay, now start at